So this video is about the unique factorization and how it can fail in other settings. So when we left off, we were talking about the integers, and today we're going to prove that the prime numbers are the multiplicative building blocks of the integers. And we're going to prove it just for the positives, but of course it's also true for the negatives. But as a warm-up and kind of a review from last time, let's consider this question. True or false? If P is prime and P divides this product here for n integers AI, A1, A2, A3, etc., up to AN, then P must divide at least one of the AI. Is this true or false? I'll pause and think about it if you'd like. Okay, so it's true. And it's true because of Euclid's lemma. So it's kind of like a generalized Euclid's lemma. And you could prove it like using induction if you'd like. It would be a good practice if you want to practice that. But today, we're going to prove the fundamental theorem of arithmetic. Theorem 6. And I like to abbreviate it, or just shorten it to fundy because it's funner to say that. Every integer n greater than 1 can be written uniquely up to the ordering of factors at least. Or as a product of primes. And we will express it this way: P1 to the E1, P2 to the E2, Pn to the En. Or I guess we should use an M here because we're already using the letter N. And here, so P1, P2 up to Pm are primes. That's incorrect grammar. Being primes. And then these exponents, E1, E2, etc., these are natural numbers, of course. And remember that the natural numbers consist 1, 2, 3, 4, 5, etc. Okay, to prove the fundamental theorem of arithmetic, so it's an existence and uniqueness proof. So let's go ahead and do existence. So to prove the existence of this form, let's suppose that it fails. So suppose not. Well, then there is some integer n bigger than 1 that doesn't have such a factorization. And we may as well take this to be the least integer like that. We can do that because of the well-ordering property. So let's let n be the least integer And I guess we should really specify, or we could specify, n is going to be bigger than 1, be the least integer that doesn't have such a factorization. Well, so in particular, this means that n isn't prime. And why isn't n prime? Well, because if n was prime, we could just write n equals n, provides the factorization. Okay, so n is not prime, and that means that we can write n equals x times y for some positive integers x and y, and each of these as a proper divisor of n, so that means they'll be less than n. But then x and y are less than n. And n is the least element that has this, that fails to have this property. So that means that x and y must have the property, so they can be factored. Combining their factorizations yields a factorization for n. And this contradicts our assumption about n being the least integer that doesn't have such a factorization. And we have existence. Okay, what about uniqueness? Well, okay, so let's suppose that n has two distinct factorizations. Or two factorizations. And let's write them n equals p1 to the e1, p2 to the e2, all the way up to pm to the em, and n equals q1 to the f1, q2 to the f2, all the way up to the q little n to the f little n. Okay. And in particular, we may as well order these. So P1 less than P2 all the way up to PM. Q1 is less than Q2. And of course, E1 up to EM and F1 up to Fn are natural numbers. Okay, so we can combine these equalities. Well, we get P1 to the E1, P2 to the E2, PM to the EM equals Q1 to the F1, Q2 to the F2, all the way up to Qn to the Fn. And what can we do here? Well, so Q1 divides n, which implies that Q1 divides this whole thing, P1 to the E1, P2 to the E2, PM to the EM. But remember in our warm-up we talked about Euclid's lemma? We can actually use that same result here to say that Q1 must divide some PI. Refer to the warm-up. Q1 divides some PI. For some I between 1 and m. And what can we say? So PI is prime, right? So that means that Q1 must equal PI. Q1 equals PI. Both of these are primes. And recall that we ordered these from least to greatest. So in particular, P1 is like less than P2, etc. We ordered the PI and the QJ. So if I is bigger than 1, then we have P1 is less than PI, of course. But by the exact same logic, P1 also divides all of this Q stuff, Q1 to the F1, Q2 to the F2, Qn to the Fn. And then that implies that P1 divides Qj for some j. And if we put all of this stuff together, we get these inequalities. So we get P1 is less than PI, which is just Q1. And Q1 is no larger than Qj, which is equal to P1. But hold up, we just showed that P1 is strictly less than P1. This is, of course, an impossibility. So what we've shown is that Q1 needs to be equal to P1. Okay, so without loss of generality now, we're almost finished. Without loss of generality, say, let's compare the exponents. Say E1 is no bigger than F1. And you just divide through by Q1 to the E1, which is the same as P1 to the E1, to obtain that E1 equals F1. Okay, and then from here you can do induction. I leave that as an exercise if anyone's curious to do that. But this gives the essence of the proof, really. Okay. So what are the takeaways from this theorem? So this theorem basically justifies us saying that the prime numbers are the building blocks of the integers. And in particular, we really mean the multiplicative building blocks of the integers. Because we can uniquely decompose any number into a product of primes. Okay, so, and this is what we mean by unique factorization. So here's a question. What if unique factorization didn't hold? Well, let's consider just a really quick example of a sort of set where unique factorization doesn't hold. I'm going to put bad in quotation marks here. And this isn't like a super rigorous example. I'm just mainly doing this for motivational purposes. So consider the set of complex numbers, and it has this funny notation, z square bracket root minus 5. And it's the set of all a plus b times root minus 5, where a, b are integers. Okay, and like, what sort of numbers even live in this set? Well, for instance, 2 plus 3 root minus 5 surely belongs to it. But something like 6 root 2 or 3/4, these do not belong in this set. And let's in particular notice that z can be identified with a subset of z root minus 5 because we can just take b equals 0. Okay, so what's the point? Well, I claim that there is no unique factorization property for this set. There is no unique factorization. Or there's no fundamental theorem of arithmetic. And this might be scary, and I will give an example to quickly demonstrate this. And by this we mean that like there are numbers in this set that have two distinct prime factorizations that actually just aren't equivalent. And by prime here, we kind of just colloquially mean unable to be further factored. So in particular, consider 6. So 6 certainly lives in this set. And I'm going to give two factorizations of 6 that are different from one another. So 6 equals 2 times 3. And 6 equals 1 plus root minus 5 times its complex conjugate, 1 minus root minus 5. And again, like, so 2 and 3 are prime. But these are prime? Yeah, just take my word for it for now. When we talk about ring theory later in this series, we will actually do a deeper dive into all of this, and it will make a lot of sense. But yeah, we can quickly verify this. We can at least verify that this decomposition works. So 6 equals, well, we can just compute this. 1 plus root minus 5 times 1 minus root minus 5. So that's 1 minus root minus 5 plus root minus 5 minus root minus 5 squared. Well, this is 0, of course. And this comes out to 5. So this whole thing comes out to 6. So we do have two distinct decompositions for 6. And just take my word for it for now that these are prime in the sense that they are further irreducible. For now, this example is purely motivational, but the takeaway is that there are sets where, like, there are structures in algebra where these like notions that we kind of take for granted, such as unique factorization, just don't hold. And that's pretty cool, maybe a little bit scary, but we will study it in depth. And that'll conclude this video's content. So next time, we're going to talk about modular arithmetic. It's a really fun topic, and it's a pretty chill thing without a lot of like difficult proofs.